So welcome to ECEN 215 Principles of Electrical Engineering, and today we're going to talk about transistor applications. This is a follow-on lecture to our introduction to transistors, and it's going to specifically get more to where you're actually going to see transistors. This is a relatively short lecture versus the kind of introduction and kind of the explanation of MOSFETs and BJTs. So various practical uses of transistors that you're going to come across in your career is simply in signal amplification. It's one of the most common things where transistors were used and still are used. For instance, operational amplifiers are primarily used for signal amplification. Also, the early days of transistors, known as the transistor radio, was some of the first products ever produced for the mass public using transistors. But again, transistors are pretty much in everything today. They're primarily used just a plethora of computing technology that we have is used in switching and digital logic systems and microcontrollers and stuff like that, microprocessors. So it's just mainly used in a lot of switching, but it is the basis for all signal amplification technology. It's also used for switching power control. Almost all your lighting, except for just turning on and off light switches, but all of you, like in your vehicle, your headlamps are turned on by transistors. Heaters are turned on by transistors. Probably a lot of your HVAC systems are controlled by transistors. The dimmer on the light switch, for instance, in your home, if you have a dimmer, for instance, for controlling the intensity of light, that is being controlled by a transistor, a type of transistor for that, usually known as a triac, but it's a transistor-based technology. So controlling motor control, just the sake of it, like a three-phase motor in a high multi-horsepower setting, that is controlled by transistors. The Tesla automobile, for instance, the motors that are used for going into ludicrous mode. And I was just actually watching a video earlier, someone actually taking a Tesla to a drag strip and watching it perform as well as it did. It was fantastic. Those motors in a Tesla are controlled by transistors. So that's a heavily used item. Of course, you also have solenoids and relay control. Again, you still use relays heavily today for also controlling power applications. And that again also is controlled by transistor technology. Again, referring back to HVACs, your compressor like on the outside of your house or apartment that's turning on your air conditioner. It probably is using a physical relay. Some of the older ones use a relay, but the actual drive of that relay, if you actually pop the electronic system out, it's going to be a small little microcontroller or small little digital logic device controlling a transistor that's controlling the relay. Heaters are effectively normally controlled by a transistor, or again, sometimes a relay to a transistor, and of course, lighting control. That's just some examples. We could probably talk for an hour of where all transistors are used, but these are just kind of a highlight of that. One of the main places that you're probably going to come across a transistor in your career is in motor control. That is a quite common place where you're going to have to actually interface with a transistor. And one of the ways motors are controlled, especially DC motors, is through something known as an H bridge. And sometimes it's a little hard to see. You're probably going to hear, if you're working with an engineer, an electrical engineer, and you're working on a control system, you're probably going to hear them say, we need to put an H bridge in a system. All that's referring to, it's basically a way of delivering current to a motor or a load. In this case, the load is a motor, in a way such that I can change the polarity. So if you notice here, I have a motor, and let's just say this is the red wire or positive lead of the motor, and this is the black wire or negative lead of a DC motor. Meaning if the current is flowing from red to black this way, the motor is going to turn, let's just say, clockwise. Now, if I'm able to flip this around and actually reverse it and I flow current going from black to red or negative to positive, now the motor is going to turn in the opposite direction. So based upon the current flow, I can have the motor go forward and backwards and forwards, which is a useful thing, especially if you're controlling position or something. Now, how do you do this is by using an H bridge. So if I turn off this transistor, and if in this effectively, if in this case, everything is off. So if all these transistors are off, the motor is not connected to anything. So as effectively, since remember we learned about MOSFETs the other day in the previous topic, if they are off, then there is no current flow. All of these RDSs are infinity ohms. So it's basically as if the motor is not connecting anything. The wires are just hanging in space. And so actually you can mechanically rotate the rotor yourself and cause, in other words, you can control it, or the application can turn the shaft of the motor, and nothing's going to happen. The motor shaft will turn. It's free to turn. It's fine. The system is truly off at this point. There is no current to actually cause the motor to turn. However, what if I do want the motor to actually turn? And I want, in this case, motor to turn in a clockwise direction. As we were saying a moment ago, let's say we have it where, get this, where this is the positive and this is the negative side of the motor. And with the current is going this way, the motor is going to turn clockwise. And if that's my goal, then what we do is we turn on this transistor, we turn on the counter transistor across the H bridge, and we're going to see why we call it that in a minute. We turn on this transistor, and current is going to flow in from VBAT, say if we have a battery here, and it's going to go through this transistor, go through the motor as we want it to go from positive to negative and turn clockwise and eventually return to the negative post on our battery. And that's exactly what we want. And notice the other two transistors, in this case Q3 and Q2, are both off. Now, if I flip it around and I wanted to go from B to A, basically, if I want to still, this is the positive and this is the negative, but now the current is going to flow this direction and now cause the motor to turn in the opposite direction. What we do is we turn on this transistor and this transistor, turn off this one and this one, and now we have a situation where the current is going to go from the battery, but now come in the negative, go across, and out through Q2. So I'm able to change the polarity on the motor just by the way I set my control values of this. Now, one of the more important things to realize that you have to do is you can never what they call short the H. And where an H bridge gets its name is the fact that you now have this kind of a symbology. So we have the A side and the B side, and then we have the load here in the middle. And hence it's known as an H bridge because you're creating the letter H where the load is in the middle of the H. Now, what ends up happening again is you have these four transistors operating in this condition. Now, the one thing that you can never have happen is this become on and this become on at the same time. That is a mega no-no. I hate to say it like that, but you do not want that to happen because when that occurs, then you short out the H bridge and causes current to go straight from the battery to the ground, bypassing the motor completely. And if you do not have a fuse here, which you usually will have in circuit somewhere, you will cause your battery either to explode or otherwise melt terminals or melt wire. So you want to make sure that you always have a condition where this is off and this is off, and where you only have basically the opposite diagonal is what's being controlled. So this is on and this is on here, all while this is off and this is off. And there's usually special chips that you can use, special digital logic circuits that will guarantee they are actually designed to, if they decide to blow, they blow in a way that causes a fail-safe application where no matter what, you're never going to get a situation where you have an on and on condition. So again, this signal and this signal are linked typically, and then this signal and this signal are separate. So this is usually the B control, and this is usually the A control. And usually you have it where A is equal to A here, obviously, and then B is usually equal to A naught, so that it's the invert of basically this. And you can't just simply put an inverter in front of that. There's some delay logic you also have to too, because even if you briefly short on, like if you have this again, if these are on at the same time, you will short. And you have to really pay attention to the fact that if in time this is the A control and this is the B control, if A is doing this and then B is going to turn on, ideally you would want to turn on right here, but if there's a slight overlap where this stayed on even briefly, since you had this little overlap here, then right in this section here, this would be a short. So that's something that is vitally important when you're designing anything with an H-bridge to make sure that doesn't occur. Another place where transistors are heavily used, again, is in solenoid and relay activation. Again, in a mechanical system, you're going to have control valves to move fluid, to move air and pneumatic systems. In fact, I was just working on a project here just a few months ago for a pneumatic air system for Texas Instruments on one of their production lines. And this is exactly what we had. We have a solenoid that would trigger, we had an air solenoid, and I had to actually turn on and off a solenoid inside here. So there's a magnetic coil here that would actually cause this valve that's mechanically in here to activate. And the way I would control this solenoid here is with a transistor. And in fact, I used a 2N7002 transistor in this particular application where I use an NMOS transistor, where this signal here on and off was 3.3 volts here, and this was simply 0 volts. So as long as I put 3.3 volts on this gate, the current would flow from 24 volts, so it's 24 volt solenoid, it would go through the coil and would continue through if I was at 3.3 volts. If I put 0 volts on here, it would be off, and then we would end up with no current flow, and so the relay would be off, causing the valve to not actuate. So basically, if I have current flowing through the coil, I would end up with airflow. In this case, 80 psi shop air would go through, and it was a ported valve, meaning that if the solenoid is off, it would stop here, so I'd have 80 psi here. And then over here, it was vented out, so we'd end up with 0 psi here. And then if I put, you know, basically had this condition here, and we were on, you would end up now where the shop air would continue through, and you would end up with 80 psi here. All simply by adding one transistor at the bottom of this. Now, one thing I added, and of course this was in my circuit I had that, for the project I released, fundamentally you just need a transistor. In practicality, remember this is a coil of wire. And if we remember what a coil of wire is an inductor. And inductors have a property where voltage is proportional to the inductance of it, again, by the change of current over time. And you go, great, why are we talking about this again? Well, this is something that comes back and can bite your circuit in the proverbial butt, so to speak, in that if you do not take this into account, you can end up with disastrous situations inside your electronics. Because this electronic condition is occurring, you're going to end up with a voltage spike. Because if I turn on this coil and I now have current flowing through the coil, now this inductor A is now going to be happy with 24 volts, whatever the resistance of the coil. Let's just pretend for a moment it is, let's pretend it's 10 ohms right now. So R is equal to 10. So now we have 2.4 amps running through here. When I turn off this transistor, this inductor still wants 2.4 amps running through it. And so it will generate what is known as back EMF. And so it will generate a reverse voltage here, which is going to affect your power supplies and your digital electronics that is controlling this. So to prevent that, you put in a capacitor here. Typically, this is of a neighborhood of about 0.1 microfarads to kind of counteract the field, kind of short out that transient spike. And also you put in a diode in the opposite direction because that voltage is going to be generated positive here, negative here. So what ends up happening is that voltage, exists now that the transistor is off, and it will short out the coil. So this is known as basically a snubber circuit that you add to your coils to prevent transients from existing on your power supplies. Now for heater control, kind of the same thing that we've had before. We also notice the same thing exists here. I've got my little snubber circuit. We use the exact same circuit, but instead of a solenoid, it is now a heater element. Now, if this was a resistive heating element, you would not need this. It's only if you have an inductive heating element or inductive type of load where you need to make sure you put this. This is also true on a relay, by the way. So all of these circuits apply. Notice again, we simply have one NMOS transistor here. In this condition, you could also use a PNP or an NPN transistor BJT, but typically today we use NMOS, and we have our gate here. Again, this is the drain and the source, and all we have to do is again provide a signal that is 0 volts up to about probably 3.3 volts or 5 volts. Now, where this signal comes from typically comes from a microcontroller, an MCU, and we're going to be talking about in the next set of topics. But a microcontroller, say like you used a Raspberry Pi or an Arduino that you can purchase and program pretty quick and easy, you can generate this signal coming right out of, like say, port 1.0 out of the processor on the little header. You literally have ground, and you connect the ground here to the ground pin here, and then you take this signal and you literally tie it to the gate pin of this, and you can actually turn on and off this heater. Now, you'll notice it sits here, it's talking about pulse width modulation. So I can turn on and off the heater. Now, in a lot of applications, we want to actually control the amount of heat we're introducing proportionally. Now, you could control the current that you're driving through here with an analog circuit. So basically, we inject a current I into this, and basically the amount of heat generated is proportional to that. In fact, it's kind of squared proportional, because remember, power is equal to I squared R, right? So if we can control I, or it's also equal to V squared over R, so we can either proportionally control the voltage or proportionally control the current, we can affect power. So we can affect the amount of heat that we're delivering to, say, a vat that we're controlling on an industrial process line. So how do we do this? I can make an op-amp circuit, for instance, to control it. The problem with an op-amp circuit is that I'm either going to use that energy either in the heater rod or in the control for the heater rod. So either way, I'm dissipating the full load. Or I do something called pulse width modulation. And what that refers to is the amount of time on that is provided. So for instance, let's pretend we have 24 volts here, and let's pretend for a moment this here was 1 ohm in size. Okay, so we end up with 24 amps because if this is just on and off, so when this is on, we get 24 amps on at 100%. Okay, now this is we have a waveform that's now, so that would be like a waveform that looks like this, where this is ground, and this is, say, 3.3 volts coming into the gate here. Again, the gate drain source. So at 100%, we're just steady, always 3.3 volts. No matter what we do, it's 3.3 volts. Now, if I have a waveform, say that this is 1 kilohertz, digital waveform, it's a square wave. And so this right here being 1 kilohertz, that means that this is 1 millisecond. And what we call 50% duty cycle, and this is dealing with pulse width. Duty cycle represents the amount of time on versus the amount of time off. So in the case of 50% duty cycle, we've got 500 microseconds over 1,000 microseconds, or rewritten 0.5 milliseconds over 1 millisecond. So we end up with 1/2, which is equal to 50%. So that's how you get the 50% duty cycle. This is referring to time on over cycle time. So that is key. Very important. So at 50%, if you do time, so heaters don't respond quickly mechanically. You know, the actual thermal energy does not respond at 1 kilohertz. Just the heat energy does not. So what ends up happening is it averages out over time. So the average ends up being I equal to 24 volts, right? Times, divided by, let's just say 1 ohms, times our duty cycle. So you end up equal to 12 amps. So you've reduced your energy by that factor. Same thing here if we go to 75% duty cycle. So by simply increasing the time on, so this total time here is still 1 millisecond from here to here, but the amount of time on has now increased. And of course, at 100% duty cycle, it's just always on. It's 100% always on. And 0% duty cycle is always off. And so you have this linear range between 0 to 100% that you can control a lot of different devices, including heaters. This is extremely common and something that you will probably most definitely guaranteed to see in your career and working with things. The PWM is heavily used in heaters, even cooling systems. Thermoelectrics use it. This is heavily used in speed control of motors. In the end, in fact, when we were talking about H-bridge earlier, you can actually control the speed of a motor by using PWM. DC to AC inverters. Basically, if you have a 12-volt battery and you want to generate 120 volts VAC, it actually uses PWM and an H-bridge and a transformer to generate 120 volts. So PWM is heavily used, and it's usually at a pretty higher frequency, 20, 30 kilohertz, but in the end, it's all about duty cycle. And again, if you notice, the overall control circuit for the element is the exact same circuit we were just looking at a moment ago. The only thing different here is this digital waveform is now a square wave at some frequency, and we're controlling the on time. The good thing is that now modern microcontrollers for the last 20 years or so, they usually have a peripheral and various peripherals, and some of them are specifically designed to just solely do this, of having multiple channels that exist to do nothing but provide PWM signals, where you provide it the frequency or the period of the signal, and you just provide basically a duty cycle to the register, basically 0 to 100% or some fraction thereof, and you can actually get some very fine control of the elements in question. And this is an important one to point out, because this is usually what I add to a test question to see if you've understand the material transistor. So this one here, I'm going to take a moment and really explain. Effectively, it's the exact same circuits we've been looking at. We again have an NMOS transistor here. We have a drain, we have a source, and we have a gate. And this again is really for me to know that you've been paying attention to this and just kind of absorb some of this information. So again, this transistor is being used in a saturated mode, such that it is simply either on or off. So we either are on or off. We may sometimes have a PWM driving this as well. But let's just simply consider in this case just simply on or off. And the question is here, what is R? What does the value of R need to be to cause this condition? So we want, and this kind of really goes back to our diode lecture, what is the value of R here? So we have 12 volts DC, and we want ID here to be equal to 10 milliamps. So we want that, and we have a forward voltage of this LED that's equal to 2.1 volts. So we can solve this simply by going 12 volts minus the forward voltage. So it's the voltage drops here. We got 12 volts, a voltage drop VR, and then we have our VF. And then the question is, what is the voltage drop across this when it's saturated? So V, V, let's just call it VT for transistor, or T, we'll just call TR, is equal to RDS, which is the resistance, times ID, which is really small. So we're talking 0.1 amps times typically about an ohm. So we're talking about 0.01 volts. So not even really worth talking about. This is, in other words, this is approximately equal to 0 volts. So the transistor is not anything of being concern. VF here is 2.1 volts, so we'll go ahead and subtract that. And then, so that's that. And if we go ahead over here, let me jump, kind of jumping ahead a little bit. So let's just work out the, if you will, the mesh loop equation here. So we got 12 volts is equal to the voltage drop across the resistor, which is VR, plus the voltage drop across the diode, VF, or the LED, plus a VTR, which we just mentioned. This is equal to 0 volts. VF is equal to 2.1 volts. And it's all we need to figure out is VR. So again, kind of resolving this, we end up with the 12 minus VF is equal to VR effectively. Again, considering that this is 0 volts. So to figure out VR is equal to R times I, in this case, ID, because that's the only current flowing here is ID. So times ID. So we need to divide this by ID is equal to R. Well, we know what ID is. It's 12 volts minus 2.1 volts. It's supposed to be 2.1 divided by 0.01 amps, which happens to work out to 90 ohms. So again, 12, we have 12, 2.1 minus, divided by 0.01, and we end up with 990 ohms, excuse me. So 990 ohms. So this will be a good one to practice learning how to get to this answer. So again, we just wrote a mesh loop equation of this circuit here. And we had this voltage drop here. We had the voltage drop across the resistor, the voltage drop across the diode, which is equal to VF, and the voltage drop across the transistor, which is approximately equal to 0 volts when on. And the reason I highlight that is that on the test, I'm going to ask you, given a transistor is on, basically, what is the current? Usually I do it two ways. I have you sometimes compute the resistance, or sometimes I give you the fact that this is on, and I'll ask you to compute the resistance, or I'll ask you if this is off, and I got the resistance, what is the current going through here? If the transistor is off, so if we're off, in other words, this is 0 volts, what is the current going through this ID? The answer to that is equal to 0 volt or 0 amps. And the reason is because right now, if this is off, this resistance is equal into the megohms. There is no current flowing through this transistor, which means if there's no current going through this transistor, there's no current going through the resistor, there's no current going through the LED, which means ID is equal to 0 milliamps. So definitely pay attention to this slide. And again, please go to the Q&A, because this is a guaranteed be on the test kind of question. So in summary, the purpose of this lecture was just giving a quick applications of transistors that you're going to see in your career, and looking at, again, the circuits for like controlling LEDs, pulse width modulation, heater applications, solenoid control valves, etc. So again, thank you for your time, and please come to the Q&A with any questions.